Hey everyone. My name's Will Lachance. I work in the engineering organization for Mozilla. I guess my job could be loosely described as working on things to make either engineers or QA people more productive, usually by automating things that would have been done by humans before, or making things that are already automated easier to access. So today I kind of wanted to talk about a system I worked a few years ago called IDA-Ticker, which sort of takes a different sort of approach to analyzing web browser performance than is usual. Just to give a little bit of background on what I mean by performance, I'm just going to talk through a few very, very basic principles. Is there a way I could get the slides on this screen? Touch screen to begin. Maybe that's... Oh, there we go. Okay. So some basic UI principles. I think everybody would know this already, but just to go through them again. First, fast is better than slow. Displayed is better than not, and smooth is better than janky. So instead of describing what these things are, I'll just show you. This is an example of something that's slow. It's us loading an older version of Fennec that was kind of crappy, loading on an old phone, trying to load Firefox. And you see that it takes about 7 seconds before everything displays, which is kind of unsatisfying from a user perspective. This is the exact same interaction, except that it happens a lot more quickly. Maybe not as quickly as we'd like, but still pretty fast, so that's better. Here's an example of something not displaying. It's a Firefox OS phone, which we're not shipping anymore, trying to load the marketplace application and not getting very far. It's better to display at least part of the application, even if you can't display all of it if you're doing an operation that's taking a long time. This is an example of a web page being scrolled in a janky manner, which is to say that the animation is kind of choppy, and there's bits of the screen that aren't being displayed because the web rendering engine can't paint fast enough. This is a similar operation happening a lot more smoothly, which is more of what we would like to see. So, okay, how do we measure these things, right? So the obvious answer is instrumented, right? Like, go into your code base and figure out how to time the operation you care about. So for example, if you want to see how long a web page takes to load, instrument the code so that you get a timestamp when you start the load operation, then have something that listens for the event when the operation is complete, whatever that means, and then take the difference, and then you have a timing, right? Pretty simple, easy to automate, we're done, right? Well, that works pretty well for some things, but I guess there's two problems here. One, how do we know that a number measures what it says it does, right? Like there's a whole boatload of assumptions baked into a system like that, that say the ending event. How do we know that things are really truly loaded when that event fires? A developer, either the testing code or the code being instrumented could be wrong in some way, and we wouldn't really know, right, if we're just seeing a number. And then the second is that there's kind of an inherent disconnect between what is measured and what appears on screen. So for example, if you're listening for an event to come in, that thing that's listening for an event might be in a different process, so there might be some inherent latency between the event being generated and us seeing the result. So this is sort of especially important when you're designing software that you're shipping to millions or hundreds of millions of users potentially, right? You want to be pretty sure that the product that you're shipping is good. So generally, when you want high quality results, the conventional QA solution is to take a high-speed camera, point it at the screen, make a movie, split the movie into frames, and then since a camera operates at a specific number of frames per second, you can sort of calculate from that exactly how long an operation takes. And then you put that number into a spreadsheet, and then you send that to your manager. And yes, there's some people who spend either a small part or a large part of their day-to-day job doing exactly this. But this also has problems, right? It's extremely time-consuming, which means that it's expensive, which means that you can't do it like on every commit. Maybe you could do it every day, But even still, like, shouldn't people be doing things more interesting than that with their time? You know, like, I think sort of part of the point of my job is that, you know, human beings are creative individuals with all sorts of potential, and they should be doing things more interesting than, like, going through video files and, like, figuring out which frame number happened when. It's not a good use of time. So what if we could get a machine to do it, right? We could get faster results, potentially on every check-in, and we could get humans to do more interesting and creative work. But of course that creates a set of new problems, as in, like, how could we possibly do this? So the first set of problems is how to automate performing the set of actions that a human would on, say, a phone, which is what iDetector operates on, and then taking the footage. And then the second is to somehow get a computer to figure out what's going on in the footage. I think they're both interesting problems, but for this audience, I'm just going to talk about the second. Talk to me if you want to talk about how to automate all this. So let's go back to the beginning. Okay, how do we measure that something like this is complete, right? All we have is a set of video capture frames. How do we extract the meaning that we need from it? What does completeness actually mean? So I guess the answer that most people give me when I pose this question is, well, we look for patterns that indicate completeness, right? Like, in this video, there's like this puzzle piece thing that comes in when we're done. So can we just, like, hook up something like OpenCV to look for the puzzle piece image and then call ourselves done when we see the puzzle piece? Well, that could work. First off, it's kind of complex, though. I don't actually know how OpenCV would do something like that, although I know it can. And then the second problem is that, like, it's prone to breakage, right? Like, if all of a sudden a graphic artist decides that it should no longer be a puzzle piece that displays when your browser first loads, all the automation is going to break, and then somebody will have to go in and fix it manually. So my solution is, let's just hack it, right? Let's just look for when the image stops changing too much. That is, compare each image side by side, compare each pixel value, see what the difference is between frames, and then just call ourselves done when there's no large differences between frames. That sort of winds up being a bunch of really easy, understandable code. I mean, it's really not that complicated, right? Like, I hope it's not that complicated. At least it's easy to understand the idea, right? Calculating smoothness, you know, like, it's the exact same idea, right? Like, if you have a low number of frames per second, you're going to have a lot of frames that are kind of identical. So just calculate the difference between the frames, see how many are unique, and then you have a rough approximation for how smooth your animation was. Kind of a similar idea, right? Like, so you're still calculating the differences, you're just calculating the number of differences over the entire length of the capture. Okay, so that worked pretty well for, like, the base case, which was where we had a fairly high-end phone for the time with HDMI out, and we had an HDMI input card, and we got a very strong signal. For the Firefox OS project, we were using low-end phones that had no such technology, so we actually opted to use a high-speed camera that could be automated and generate ugly, grainy video like this. So the thing here is that with a video like this, you're going to have a lot of differences between frames, pixel differences between frames that don't actually represent a qualitative difference between in the content of the frames, if that makes any sense. So how do we solve this? I actually went around a little bit before I realized that we could basically just look at the information content of the frame, which actually doesn't change that much between frames. So, like, that is to say, even though the pixels inside a frame might change a lot, like, just because there's a varying amount of light that's hitting the camera sensor at any given time, the overall information content is going to stay roughly the same. And that's pretty easy to calculate using Shannon entropy. Just think of it as, if I were to gzip that picture, how well would it compress? And we can measure that per frame. And that worked pretty well for that use case. So I guess the question that comes up, is this type of automation just cheating, right? Like, are we, this is pretty far from what a human is actually doing when they're looking at a mobile phone. So like, are we actually doing any better than the sort of synthetic benchmarking that I was criticizing earlier? I would say we are, I would say like, I claim that my technique works really well. Empirically, it seemed to work pretty well. But if you, I think more importantly, even if you don't believe me, even if you think my assumptions or my math is wrong or silly or I'm an amateur, you can at least look at the movie and see what's actually going on, right? Like, you don't have to take my word for it, or you don't have to take my code's word for it, which I think is really valuable, right? I think building systems that you can sort of trust end to end in that sort of way is really, really powerful. And that's sort of all I wanted to say. I mean, I guess the sort of lesson is, sometimes problems are, if you look at them from the right angle, they're a little bit easier than you think they are. And also that, like, let's get machines to do things that are boring and humans to do things